So what happens there is that first two nuclei of helium-4, here is a proton, here is a neutron, this is one nucleus of helium-4, and then there is another one. They fuse together, first giving the nucleus of beryllium-8. And this beryllium-8 actually does not last very long. It decays back to the two helium nuclei in about 10 to the minus 19 seconds, okay? However, the temperature is so high that the third nucleus of helium-4 can actually fuse quickly with the nucleus of beryllium-8. So here we have the fusion into the nucleus of carbon-12, plus, of course, energy. And this nucleus consists of 6 protons and 6 neutrons. And it's called triple alpha process because it turns out that a particular kind of radioactive particles that are emitted in radioactive decay of certain unstable nuclei, first termed alpha particles, are nothing else but the nuclei of helium-4. So the net result is that 3 of those are fused through this intermediary step into the nucleus of carbon-12 with the release of energy. The onset of this fusion is often referred to as helium flash. And the star enters so-called yellow giant stage. It turns out that the energy released during this helium fusion per reaction is less than the energy released in the reaction involving the fusion of hydrogen. Well, what that means, it means that in order to create enough energy and enough pressure to support the star, the rate of helium fusion into carbon has to be very, very high. We need to fuse many more nuclei of helium to generate the same amount of energy that would be released through a fusion of a certain number of hydrogen nuclei. Okay? And so the helium is burned, so to speak, at much higher rate. And for that reason, this stage, the yellow giant stage, doesn't last very long compared to the main sequence stage. It lasts maybe for a star like our sun about 100 million years. Compare that to 10 billion years, which is the entire lifespan of the sun when it is a main sequence star. And the reason is, as I said, the energy released per single helium fusion reaction is smaller than the energy released per single hydrogen fusion reaction. Okay? And as a result, the overall rate of helium fusion has to be much higher than the rate of hydrogen fusion to generate enough energy in order to support the top layers, right? I mean, if you have one 100-watt bulb, right, then you'll need 100 1-watt bulbs to produce the same amount of energy. The same is happening here, right? The 100-watt hydrogen bulb would, light bulb would correspond to the energy produced in hydrogen fusion, and 1-watt light bulb would correspond to the energy produced in the single helium fusion. Okay? So you need to burn more helium nuclei in order to generate equivalent amount of energy. So the net result is that helium is fused into carbon much more quickly, and in, as I said, roughly 100 million years for a star like our Sun. And on the other hand, the main sequence stage, where the hydrogen is fused steadily into helium, is much longer, 10 billion years. Now, these facts of nuclear physics, how much energy is released per helium fusion vis-a-vis hydrogen fusion, if you think about it, they have very important consequences for the existence of life. Okay? Suppose that there was no hydrogen fusion, that the source of energy in stars was only helium fusion, where the stars would last only 100 million years. Okay? Then, if these stars had the planets, there would be not enough time for the life to evolve on those planets. Okay? So the fact that the lifetime of the Sun is on the order of billions of years is important, because there is enough time for the life to evolve on a planet like Earth. Okay? So think about it. The basic laws of nuclear physics have direct implication on the evolution of life on Earth. Okay? Also, you know, the carbon, we are, the organic materials like us involve carbon compounds. This is how the carbon in the universe is produced. However, in a low-mass star, as you'll find out later on, basically this carbon remains trapped in a dead core, right? It's localized there. It's not dispersed throughout the space. And it turns out that carbon gets dispersed throughout the space when high-mass stars, which also produce carbon and heavier elements in the process, eventually explode in a supernova event, and that material that was synthesized in the belly of the star gets dispersed throughout the universe, is mixed into the interstellar material, gas and dust. Most of it is 3/4 by mass is hydrogen, 1/4 helium, and there are small amounts, a few percent of everything else, okay? And that everything else was actually synthesized in stars. So the Sun, once it dies out completely, will not make its carbon available to the rest of the universe. It will stay trapped in the dead core, which is in fact what constitutes the white dwarf. So why does the star becomes a yellow giant? How does it change from the first red giant phase into this yellow giant phase? Why does the color change? It also is reduced in size. Well, the reason is as follows. I'm just giving you sketches, the most important things that you can perhaps follow, leaving many details out, because there is no point in discussing those things as you don't have enough background. But basically, it's something like this. Okay, so much energy is released after the helium flash that actually the core heats up and expands. This gas in the core, carbon, helium, heats up and it expands. Because of this expansion of the core, its edge actually cools down. But remember, there was that hydrogen fusing shell surrounding the core. And because the temperature, the hydrogen was fusing profusely because it was in direct contact with this very hot and shrinking core, right? the rate of hydrogen fusion in the shell is much higher than the rate of hydrogen fusion in the core of a main sequence star. But now the edge of this core cools down, right? Which means that the temperature in the surrounding shell drops, and the fusion of hydrogen in the shell stops. And remember, during the first red giant stage, that was the main source of energy of the star. That's where the only energy was generated through nuclear fusion. Some energy, of course, was generated via conversion of gravitational energy into thermal energy as the helium core was contracting, right? But the main source of energy was in that hydrogen fusing shell, and now it's turned off. This causes the pressure that was created by energy generated in the shell to drop. Remember, it was that pressure that pushed out the top layers of the sun or the star. As a result, the top layers start dropping. The size of the star starts reducing. Okay? And as it starts to shrink, its surface is now getting closer to the energy-producing core, and surface warms up. Its temperature goes up, and as a result, the color changes from orange-red into yellow. That's why they have it. The star in this stage has yellow appearance. Okay, and as a result, the color changes from orange-red into yellow. Okay, remember the wavelength at which a source emits a body like a star or any other object. The wavelength at which it emits most of the energy depends on the surface temperature of the source. And the higher the temperature, the lower the wavelength, right? So as the temperature of the surface increases, the wavelength at which most of the energy is emitted is reduced, corresponding to the change in color from red to yellow. Yellow light has a shorter wavelength than the red light. I linked this one before when we started discussing the life story of medium mass star like our sun. So we have here main sequence, the sun today, roughly halfway through its main sequence. And here is the first red giant stage when the sun will expand up to about the orbit of planet Mercury. And there, during that stage, we have dead, meaning non-energy producing helium core. Eventually, that core gets hot enough, it reaches the temperature of 100 million degrees. Helium ignites. We have helium flash when the helium starts fusing into carbon. The star enters its yellow giant stage. So you see it's reduced in size somewhat because of that drop in pressure. And as the surface gets closer to the energy-producing core, it heats up, and therefore the color changes from orange-red to yellow. And eventually, I said that this yellow giant stage for a star like our sun would last about 100 million years. Eventually, all of the helium in the core is fused into carbon. And a star like our sun does not have enough mass to squeeze now that carbon core and heat it up to the temperatures that are needed to fuse carbon into heavier elements. And basically, the star is done. All fusion reactions in the core have stopped. The star enters the final red giant stage, where now it has dead carbon core. So usually any kind of red giant stage involves a dead core that is not fusing a nuclei in it and producing energy in the process. Okay, so eventually all of helium in the core is fused into carbon, and a star like our sun doesn't have enough mass to squeeze this carbon core and heat it up so that it would start fusing into heavier elements. And the star enters the final red giant stage, and its life has basically expired. Okay, so this diagram illustrates the structure of the star during that final red giant stage. Here is this dead carbon core. I should mention that also there are some nuclei of oxygen, but carbon is most dominant because a nucleus of carbon-12 can fuse with another alpha particle that is the nucleus of helium to form the nucleus of oxygen-16. Okay? So there are some, there is an admixture of oxygen nuclei as well, but it's mostly carbon. By the way, that's how the oxygen that we breathe is produced in the universe. It's synthesized in the stars when a nucleus of carbon fuses with another nucleus of helium-4, and they form the nucleus of oxygen-16. Okay, so this gives, this is based on calculations. This gives the diameter of the sun in its final red giant stage. You see that the diameter would be about 400 million kilometers, and it would expand all the way to the orbit of planet Mars. And the distance, present distance, between the Mars and the sun is 1.5 astronomical units, right? 1.5 times our distance from the sun. So the sun would swell up in that final red giant stage up to about orbit of planet Mars. In the process, it would swallow the planets that are closer to it: Mercury, Venus, Earth. Now, it's not quite certain that indeed the Earth would be done, because in this process, due to stellar wind, the star is losing mass. Some of the mass is being, as we'll discuss, is being pushed out. Now, you know that the mass, the force of gravity between two objects is proportional to their masses. So if the mass of the sun is reduced, the force of gravity that is keeping the Earth in the orbit around the sun is reduced, and actually the Earth might move to the higher orbit, so to speak. Its distance from the sun could increase, okay, beyond this danger zone here, right? But as I've discussed before, this is not the actual end. The actual end will be much sooner when, as the luminosity of the sun increases over time slowly. We discussed that in detail. In about 0.5 to 1 billion years, it will produce so much energy that the temperature on Earth would be such that all of the liquid water would evaporate, right? And that's it. So we don't need to wait until 4.5 to 5 billion years from now for this to spell the demise of the Earth. Okay, so here we have now this dead carbon-oxygen core that is shrinking and heating up, right? It's shrinking under its own gravity. It's very dense. As we will discuss, the density of the core of a dead star like sun is about 1,000 kilograms per centimeter cubed. That is very, very large. Nothing that we know of here on Earth, except perhaps the density of nucleus, which is much higher, but we have no experience of that. 1,000 kilograms per centimeter cube would be equivalent to sort of compressing, say, a smart car, right, or a Fiat 500 into a little cube 1 centimeter on the edge. That's how dense these objects are, right? So we have this shrinking and heating carbon core. It is heating, but the temperature is not high enough for the heavier nuclei to be fused. Surrounding this shrinking carbon core, we have a helium burning shell. Just like we had in the first red giant stage, a hydrogen burning shell surrounding the shrinking helium nucleus. Now there's a shell surrounding this contracting carbon-oxygen nucleus where helium is being fused into carbon, and as carbon is being fused in the shell, it gets dumped into this dead core, so that the mass of this carbon core actually increases because more and more carbon is dumped into it, right? So we have this helium fusing shell, and as I mentioned, basically the edge of the nucleus is not hot enough, so that we have this dormant hydrogen burning shell, right? But nevertheless, now enough energy is produced in the helium burning shell so that the pressure increases and pushes out the top layers of the sun, well, sun. Once upon a time it was a sun, now it's in final red giant stage. As these top layers are pushed out, they get at a greater distance from the energy producing region. Therefore, their temperature drops and the color changes back from yellow to red. It becomes a red giant again.